This is going to be chapter 7, which is about chemical quantities and reactions. So in this chapter, we're going to talk about equations, how to write and balance equations. We'll also talk about different ways to classify reactions, which I think is the topic of this week's experiment. So that should be good as well. Then we'll do some calculations from the equations and stuff like that. And let's get into it, I think. Yeah. All right. So this is a balanced chemical equation. And when we do write equations, always, as we will talk about a number of times, you want to make sure that the equation is always balanced. So sometimes you are given an equation that is balanced. Sometimes you're given what's sometimes referred to as the unbalanced equation. Really, the first thing you should always do when you see an equation is to make sure that it is balanced. And if it's not balanced, you should then balance it yourself, because pretty much any type of calculation that will involve an equation, or usually whenever you use an equation in chemistry, it always does need to be balanced. So that should always sort of be the first thing that you think about when you do see an equation. A, is it balanced? And B, if it's not balanced, then you need to make sure that you go do that. What do we mean by sort of balanced equation? It simply means that on both sides of the arrows, we basically have the same number of elements, basically the same number of each atoms of those elements. So for example, here on the left-hand side, we have 2 times 2, and you would sort of multiply them together. That would give us 4 hydrogens on the left-hand side. We also would multiply this 2 to the 2 there, and that would give us 4 hydrogens on the right-hand side. This represents 2 oxygens on the left. This 2 in front, which is a coefficient, does go to everything behind it, and it would also count for the oxygen as well. Remember that in chemistry, if you do not see a number, it's assumed basically just to be 1. So there where we just see H2O means we just have 1 oxygen, since there's nothing written next to the oxygen, and that would give us our 2 oxygens on the right-hand side. Also, these are the subscripts, right? And the subscripts always go to the element to the left. So that's always, what the number counts for. The reason why this is important is this is really the law of conservation of mass, which means in a chemical reaction, we don't create nor destroy any sort of matter, if you will. And really, when we have a chemical reaction, the absolutely only thing that is basically occurring is everything on the left-hand side of the arrow, we're just going to break all those bonds. And everything on the right-hand side of the arrow, we're going to make bonds. And making and breaking bonds is what was the topic there at the end of last chapter, which is bonding. And those are only electrons being involved in that process. So as we talked about in an earlier chapter, remember that out of protons, electrons, and neutrons, which one is most important in terms of which element it is? It is the protons, right? The atomic number from the periodic table. It is everybody has their own atomic number. So because in a chemical reaction, the only thing that we play with are electrons and bonds, we have the same number of elements we start with, should be the same number of elements we finish with. They're just, in some new sort of compounds, are molecules on, say, the right-hand side of the arrow. So when we look at an equation, there's a couple of parts to an equation. On the left-hand side of the arrow, those are what are referred to as our reactants. So in this case here, on the one that I scribbled, so I'm going to get rid of all the stuff I just scribbled, I think. So these guys on this side, these are our reactants, and those are our starting material in a chemical reaction. Those are basically the guys we're going to break all those bonds away from. They're going to release basically the hydrogens and the oxygens from each other. On the right-hand side of the arrow, these are what are we called products. And so on the right-hand side is our products. And those are obviously the things that are formed as a result of a chemical reaction. So always reactants to products. Left-hand side reactants, starting material, right-hand side there, products. Now, there's other things that we oftentimes will see in equations. For example, next to formulas, we may see S written, we may see L written, we may see G written, and we may see AQ written. That means that substance is in the solid state if it's an S. It's in the liquid state If it's an L, it's in the gas state. If it is a G next to it, and it is the aqueous state, is what the AQ stands for. Aqueous basically means a water environment. It is really a solution. So like all those bottles that you probably use in lab that are just solutions, liquids, those are really solutions or aqueous type things. Now there is a difference, by the way, between L, which is a liquid, and AQ, which is aqueous, which is a solution. The difference is, just quickly, sort of the example is, if you had something like water by itself, that would be considered a pure liquid. So that would just be just water by itself. Nothing else basically in there with it. Now, if you took something like water, which is a pure liquid, and you took some solid sodium chloride, the sodium chloride would dissolve in the water. The salt basically will dissolve in the water, and you will get a sodium chloride solution, which is aqueous. So really a solution is a mixture, and it's a result of two things together, and that's basically, a lot of times, water is the big part of it. As we'll talk about in a later chapter, water is considered here the solvent, which is the larger part of the solution. In this case, the sodium chloride is considered the solute, which is a smaller part of the solution. So there is a sort of distinction between something that's aqueous and something that is a liquid, although when you look at both of them, they both are in the liquid states, but they are different. One, again, is a sort of a pure substance, and one is not. Other things that we commonly will see sometimes in equations is there would sometimes be things written on top of the arrow. And for example, very commonly we will have a catalyst written. Not really just a word, catalyst. Usually they'll do some type of symbol, like for example, platinum or H plus, which means it's an acid catalyst. What a catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. Really, the sort of only thing that a catalyst normally is there for is it will actually typically speed up the reaction. So usually, very commonly on top of the arrow, you'll sometimes see things written, and that's just there as a catalyst that will oftentimes speed up a chemical reaction. Again, it's not a reactant or product. It does so really by, for example, it finds an alternative way for that reaction to sort of occur, a more efficient way. So for example, let's just say you had gas molecules flying around. In order for that reaction to take place, they got to eventually come in contact with each other. So they got to actually collide with each other. They actually do have to hit each other with the right amount of energy for a reaction to take place. Now, let's say you throw a catalyst in there like a metal, where the gas molecules are maybe attracted towards the metal, and now they're going to be very close to one another a lot quicker, and that's going to speed up the reaction, rather than without the metal there, they're just flying around, trying to find each other. So sometimes it's as simple as it sort of provides a place where everybody could kind of get together in a more efficient way for that reaction to basically take place. Other things that we sometimes see on top of the arrow, we sometimes will see a delta symbol or a little triangle. That usually will mean heat is being applied. And lastly, occasionally we will also sometimes see like something like water written on top of the arrow, and that usually would involve you're dissolving something in water, like the sodium chloride example. You could have something like solid sodium chloride, put a little water up there on the arrow, and then you get a sodium chloride solution, basically. So you're basically dissolving that solid in water, and it's going to make a solution. So this brings up two things about equations. I would say 9 times out of 10, a lot of times we use chemical equations to represent a chemical change that's happening, a chemical reaction that is taking place. But you could also use an equation to represent a physical sort of change, just like we could use an equation where we take water to water here. Yeah. What is the difference between these two waters? Yeah, the guy on the left is water in the solid state, which is ice, right? The guy on the right is liquid water, right? So this is really showing the process of water or ice melting, right? So we can use equations to represent sort of physical sort of processes that are occurring, but a lot of times we do usually represent chemical changes or chemical reactions taking place with equations. Any questions on that there? Yeah.
Those two don't react, but let's say I put heat to them in the product, am I going to get two separate elements or?
So it does depend on what you're doing. You might not get much with those two, to be honest with you. But it does depend. And after we talk about sort of balancing these equation, we're going to talk about different types of reactions. And a lot of times there's a few major different types of reactions that take place. And based on sort of what you're starting with, you can make a pretty good prediction as to what you'll get on the product side. So just hang on, and shortly we'll get to those different types of reactions.
When I apply the heat,
Yeah.
Is the product, is that a physical or chemical reaction?
So if it is a change that results in something new being formed that is fundamentally different than what you started with, it's a chemical change and a chemical reaction. Yeah. So like for example, if you took iron and you took oxygen, right, and a little bit of moisture, you'll get iron 3 oxide, which is rust. And that's an example of a chemical change, a chemical reaction happening, because with the rust, you can't do anything physical to it to get back the iron or the oxygen in the original sort of form. Now, when you take something like ice, right, in this case, that melts to liquid water, you can just take the liquid water, throw it back in the freezer, and you will have your ice back, which is a physical change. So it goes back to, I think we covered that in like chapter 3, was it maybe? I think when we talk about sort of physical changes and chemical changes. And I would say most of the time we do use equations to represent chemical equations and chemical reactions and chemical changes, but you can definitely use equations to represent physical processes that are occurring. So I would say probably most of the time when you see, especially in this chapter, most of the time when you see a chemical equation, is probably representing a chemical change and a chemical reaction occurring. Question? Yeah. The difference between them is a liquid is a pure substance by itself. So just like water by itself, nothing else with it. And when you take something like water and then mix something like, say, salt with it, it will make like a sodium chloride, which is a solution. So a solution is really a mixture, which I think was also maybe in that chapter 3, I think as well, is a mixture, basically 2 or more substances together. And that's basically what a solution is, as it's aqueous. And most of the time, water is a lot of times part of it. And a lot of times you're just taking something that you could dissolve in water to make a solution. But something with an L is just like one substance by itself, nothing else there. Yeah. Other questions? All right, so let's talk about balancing equations. And as I mentioned before, pretty much that's always what you want to make sure you start with, is the equation being balanced. So there are multiple sort of ways that you go about balancing an equation. We're going to talk about some here, but I'm going to be honest with you, most people roll with a trial by error type thing in terms of balancing it. And I usually, as we'll go through some of the examples, think about, what is sort of the easiest thing to kind of fix and balance. And that's usually sort of a good path to start with. But there are different ways to sort of do it. The first thing, though, that you definitely want to make sure that you have is all the correct formulas down first. And what I mean by that is sometimes you may be given everything in words, or you may just have reactants that you need to maybe predict what's on the product side. So sometimes what people do is they try to balance and write formulas on the right-hand side of the arrow, and they usually will end up with the wrong formulas, and the thing will never balance. You'll be there all day trying to balance something that's never going to balance. So just keep in mind that if you have a situation like that where either it's in words or you just got like half of the equation, you need to kind of figure out based on the type of reaction what you get on the other side. The order at which you want to do it is get all the correct formulas down first, regardless of the balancing. Once you have all the correct formulas down on both sides of the arrow, then you should go back and balance it. You should not try to do that at once, because you usually will get the wrong sort of things. The way we write formulas for the most part for chemical equations is just like we talked about in the previous chapter. If it's ionic, right, we need to balance it out to 0, right, and no charge, the cation and the anion. We want to start with the right formulas. And that would represent your unbalanced equation. Once you have your unbalanced equation, you want to start balancing the equation by adding coefficients. And what I mean by that is when you have an equation, the only thing that you could change while you are balancing equations are the numbers that come in front of the formulas. That's absolutely the only thing that you could change. You should never change any of the little subscripts. Why would I not want to change a subscript? Like if I had water like this and go, oh, I just need 1. Let me just change that to 1. Why would I not want to do that? That's no longer water, right? So we would change what it is. So you should never, ever change the little numbers and formulas when you're balancing an equation. You should also never do any weird things that people, I don't know why they do it, but they're like, oh, I need 3 oxygen. I'll just like throw a 3 in front of the O or something big like that. That doesn't exist either. Yes, for those are going to get X's. So don't do any of those things. So it should only be the coefficients that come in front. When we do put a number in front, for example, like we were talking about in the previous equation, if we did have a 4 or any type of number in front of it as the coefficient, again, it does count for everybody that is behind it. So it does sort of count when you're sort of adding everything up, it counts for everybody behind it. So you want to start with, I personally think it's a good idea to start with whatever looks easiest to put a number in front to balance it out. I personally also make a table before I begin of, you know, the elements and how many we got on one side of the arrow, how many we have on the other side of the arrow. And a lot of times that helps you sort of focus in on what's a good place to start with in terms of balancing it. Once you do that, you're going to throw some numbers on one side. You'll probably need to throw some numbers on the other side, back to the other side. What's going to happen as you start to balance an equation is you'll fix one thing and pretty much screw up everything else. So then you'll have to kind of go back and fix things along the way. Eventually, though, if you do it correctly, you should end up with a balanced equation when it's all said and done. When you have a balanced equation, there's really 2 things you need to make sure of. All of your coefficients do need to be whole numbers, and they do need to be the simplest set of whole numbers. So whole numbers are pretty straightforward. They always got to be whole numbers. The simplest set of whole numbers means something like this. If I balance this equation, 2a plus 4b goes to 6c, let's just assume it's balanced. I could do what with all those numbers? I could divide them all by 2 and still get whole numbers. And that's what you would want to do. And your properly balanced equation in this case would look like this, for example. So that definitely does occur because sometimes people can see larger numbers to get everybody balanced, right? And, you know, you just got to make sure at the end, if you could go through all the coefficients and still reduce them down and get whole numbers, you need to do that to have the properly balanced equation. Any questions on that there? All right. So let's take a look at one here together, and I'm going to just show you sort of what I would do in this case. I'm going to rewrite it first. That's what I'm going to do, I think. So I'm going to go with NO and H2. Go NO plus H2. Give me a little bit more room for my coefficients I might want to write, right? And we got there N2, H2O. All right. N2 and H2O. All right, so if I have this equation, I'm going to go balance this by, like I said before, I'm first just going to make a very simple table. I got the reactant side, got the product side, and I got my elements, nitrogen, oxygen, and hydrogen. So I'm just going to add up what I got going on each side. So for nitrogen on the left-hand side, we have 1. Right-hand side, we have 2 nitrogens. Again, that number goes to the guy to the left, obviously. On the left-hand side, we have 1 oxygen there. Over here, we have 1 oxygen there. On the left-hand side, we have 2 hydrogens there. And on the right-hand side, we have 2 hydrogens there. Once again, that goes to that guy, and this goes to that guy. So this table is a nice way to do it because it just organizes everything for you. And now we can clearly see everything is balanced except for nitrogen. So that seems like a really good place to start. So I'm going to balance the nitrogen. Remember that when we're balancing this equation, we are only going to put coefficients, which are numbers that come in front. So to get me a 2 nitrogens, I'm going to put a 2 over here on the left-hand side. At that point, once again, we're going to figure out what we just did. This 2 goes to this nitrogen, and it goes to the oxygen behind it when we're counting. So that's going to give me 2 nitrogens. Now I have 2 oxygens. I still have 2 hydrogens. And clearly everything on the right-hand side didn't change since I didn't put any numbers on the right-hand side. So it's still the same. At this point, just like I mentioned, we fixed nitrogen, but we then kind of screwed up the oxygen, right? So we can still see our hydrogen is still good. So clearly at this point, oxygen would be the next easy thing to go fix. And to fix the oxygen on the right-hand side, I have 2 on the left, 1 on the right. So I'm going to put a 2 there on the right-hand side. And that's going to give me 2 nitrogens. Once again, this 2 that I put up there will go for everybody behind it. Gotta get rid of some of these scribbles here. So that 2 is going to go to the hydrogen and also the oxygen there. So that means that I now have 2 oxygens on the right, and I have 2 times 2, which is 4 hydrogens now on the right. So I'm getting closer. I now fixed the top 2 again, but screwed up the bottom one. But that could now be easily fixed by going back to the left-hand side. And all I need to put is a 2 right about there. And now that would give me 2 times 2, which is 4. I still have my 2 nitrogens and my 2 oxygens. And now we have basically the properly balanced equation. So as you can see there, the only thing I changed are the coefficients. I really went with sort of what is easiest. A lot of times you want to go with what's easiest. What's in one place on each side is the best idea, not things that are in multiple parts on each side. And just to kind of keep it simple there. Any questions on that one there? Okay, let's take a look here. So once again, I'm going to make a table. Going to list all my elements. So I got carbon, hydrogen, and oxygen. Going to keep track of what you got going on the left here. Reactant side, got 3 carbons. Right hand side, got 1. Left hand side, I got 8 hydrogens. Right hand side, I got 2 oxygens. I have 2 on the left. How many oxygens I got on the right? I do have 3. I have 2 here plus 1 more over here, right? So that is 3. So in this case, not much balance. So once again, I personally would go with what's sort of the easiest to me. Carbon seems pretty easy to balance there. Might as well start with that. We got 3 on the left, and we just want to make 3 on the right. So we're going to put a 3 in front of the carbon on the right-hand side. That's going to give me, once again, this guy is going to go to both of these elements that are behind it. So that's going to give me 3 carbons. In terms of hydrogen here, we still have 2. Now in terms of oxygen, we have 6 from the first one, right? And we still got the 1 over here, which gives us 7 at this point. Yeah. Any questions on that there? Well, we balanced the carbon, and clearly the hydrogen and oxygen are still not balanced. So where should I go next? I'm going to say the easiest one to fix, do you think, is the hydrogen or the oxygen? The hydrogen. And the reason I would say that is hydrogen is only in one thing on each side, right? On the right-hand side, we got oxygen in a couple of things, right? So you might want to save that for the end, right? So I would work with only things that are sort of in one thing on each side of the equation. So to fix the hydrogen, we would go with a 4, I think. And once again, that is going to be distributed to both of the elements that are behind it. That means here we do have 3 carbons. 4 times 2 is 8 hydrogens. And now in terms of our oxygen, we still got 6 here, but now we just added 4 times 1, which is 4. And that's going to get us up to 10 at this point. And this is also why we saved oxygen for the end, because now it's going to be easy to fix it by going to the left-hand side here, right? And all we have to do now is put a 5, right? And we'll do that and pop us a 5 right there. And that's going to give us 3 carbons over here, still 8 over here. And again, 5 times 2 is 10 in this case. And now we are balanced. Any questions on that one there? So again, this is the approach you kind of want to do. Kind of go from what seems easiest, maybe save the little complicated things for the end. There are people that say you should start with the most complicated and stuff like that. So it does depend sort of on the situation, but definitely I would go maybe with what looks easiest there. All right, let's take a look at some more here to make sure. All right, right, the balance equation for diboron trioxide reacts with water to make boric acid. We should know this from the last chapter, right? Diboron trioxide is a type 3 compound, right? So that should be like a D2O3. B2O3 would be better for boron. Reacts with water, which is H2O, and makes our boric. All right, let's take a look and see. Once again, I'm going to make a table, which a lot of times is hopefully very helpful. We got boron, oxygen, and hydrogen. On the left-hand side, we have 2 borons. On the right-hand side, we have 1. Left-hand side, we have, in terms of oxygen, 3 here, and we don't want to forget about the 1 over here, so that is 4. Now, this is parentheses, right? And the 3 on the outside, which means the 3 does get distributed to everybody inside, which means we do have 3 oxygens on the right-hand side. Left-hand side, we have 2 hydrogens. And once again, that 3 distributed in would give us 3 as well. Any questions on that so far? Not a lot to work with here. So we have everything bundled together there on the right-hand side, right? So that is probably where we should start. We're going to start with boron, which seems the easiest. I'm going to put a 2 in front. And that is now going to give me 2 borons, as this goes for this guy. By the way, it also goes for that guy and that guy as well. Everybody behind it gets the benefit of the coefficient. That means when we look at the oxygen, we got to multiply 3 times 1, which is 3, and then also multiply it by 2, which gives us 6, right? Same thing here, 3 times 1 for the hydrogen, times 2 is 6. The reason for that is if you just want to write it out, that means you have 3 of these, right? And you got, and 2 in front means you actually got another set of them. So 1, 2, 3, 4, 5, 6 hydrogens and 6 oxygens basically out there in front, obviously with our 2 Bs right on each side. All right, so clearly nothing to play with there on the right-hand side at this point. So we're going to go back to the left-hand side, and we got hydrogen and oxygen again. In this case, I'm going to go with the hydrogen, as it's just in one spot over there on the left-hand side. Once again, here we have oxygen in multiple places, so I'm going to kind of save that for the end. So I'm going to fix the hydrogen, and to fix the hydrogen, I would need to put a 3 here in front of the hydrogen. That's going to give me now 2 borons. In terms of oxygen, I have 3 here. This 3 goes to both of these guys, which means I also have 3 here, and that's going to give me 6. And 3 times 2 is 6. So in this case, which oftentimes happens by fixing the hydrogen, it also fixed the oxygen on that side. So sometimes things just fall into place if you sort of balance it sort of correctly in that way. Any questions on that there? Once again, here I chose hydrogen before oxygen because only in one place on each side. So, and obviously at this point, we do not want to go backwards, right, and take that number off and start using different numbers and stuff like that. Any questions on that one there? All right. Let's take a look at another one here. Here we go. Balance this guy up here. NH3, O2. Okay, so let's take a look, see how you're doing. We'll make a table here. We got our reactant side, our product side. In this case, we have nitrogen, hydrogen, and oxygen. On the left-hand side, we got 1 nitrogen. Right-hand side, we got 1 nitrogen. Left-hand side, 3 hydrogens there and 2 there. And left-hand side, 2 oxygens there. And we have an oxygen there and an oxygen there, which is 2. So on the face of it, doesn't look too bad. We only got hydrogen there that's not balanced. We have 3 on one side and 2 on the other side. In this case, we'd want a common number of 6, right, to kind of get them balanced. So in this case, we will have to put a coefficient on both sides actually here to start, which is okay. So to get my hydrogen on the left-hand side to 6, that's going to require me to put a 2 there. To get my hydrogen on the right-hand side to 6, I'm going to need to put a 3 there. That will give me, in terms of nitrogen on the left, again, this guy goes to everybody behind, so does this guy. That's going to give me 2 nitrogens. That will give me 6 hydrogens, and now oxygen 2. Right-hand side, 1 nitrogen, 6 hydrogens, and we do have 3 oxygens there, plus 1 more here is 4 at this point. Next easiest thing to balance between nitrogen and oxygen is going to be the nitrogen, as it's in only one spot on each side. Again, we got oxygen and a couple of spots there on the right-hand side, so we might want to save that maybe for the end. So to fix the nitrogen on the right-hand side, we need to put a 2 in front of it, and that also goes to the guys behind it, and that will give me 2 nitrogens, still 6 hydrogens. Now, in terms of oxygen, I do have 2 here for the first one, and I still have 3 here for that one, which is 5. Any questions so far? Clearly, I do not want to remove numbers, right? So I only got one place to go left, which is my oxygen, which I've been saving for the end. I basically need to turn the guy on the left there into a 5, right? Which is what we need, but we have 2 to begin with. So we should clearly at this point just go to the next problem, because this is not the right thing to do. No, I'm just kidding. Don't do that. So we need to turn a 2 into a 5. We could do that by, we could actually use a fraction, say something like 5/2, right? And if I do that, that will give me 2 nitrogens. That will give me 6 hydrogens. And when I take 5 halves times 2, 2's cancel and gives me 5 oxygens. Is that okay to leave it like that? What do you have to have when it's all said and done? All the coefficients need to be whole numbers. That is not a whole number, right? So this is just a good point. You can use a fraction to balance the equation, but you cannot leave it with a fraction. So we do have to clear the fraction. I think we do that by multiplying everybody by the denominator, right? The guy on the bottom. So we're going to take everybody here, and we're going to multiply it by the denominator, and that will then give me 4 NH3. My 5 halves times 2 is 5O2. Will give me 4 NO and 6 H2O in this case. And if I didn't screw up here, we should still be balanced and now have all whole numbers. So we have 4 nitrogens on the left to go with the 4 on the right. So that's good. We have 4 times 3 for the hydrogen, which is 12 on the left. 6 times 2 is 12 on the right. 5 times 2 is 10 oxygens. And we have 4 oxygens in the first one, 6 in the second one, which gives us 10. And now we do have a balanced equation that has all whole numbers. So it does oftentimes happen in a situation like this where you got like an element and a couple things on one side, and kind of like the diatomic version of the element, like O2, N2, those type of things by itself on the other side. So sometimes that does happen. Not always, but it does happen. So you could definitely use a fraction. You got to get rid of the fraction. So sometimes people think like maybe it's hard to determine what fraction to use. There's a really simple way to do it. The number up on top is the number you need. So if you remember, we needed, before I crossed it out, 5. So that's what went on the top. And on the bottom, this number should always match that number, and you'll always pick the right fraction. So the number you need up on top and the number on the bottom should match the diatomic little subscript, probably going to be a 2 in most cases, and you will pick the right fraction. But again, you do need to clear it when it's all said and done. Question on that one there? Well, you know, maybe a little-ish. Other questions on that? All right. So I'll talk about a few more here. Let's say we had something like this. We'll do this one. Why not? PB NO3 2 plus a little KI. Gonna make PB I2 plus KNO3. So let's say we wanted to balance this equation here. Now, when you have an equation, and especially when you have an equation that has everybody's favorite thing we talked about in the last chapter, which is polyatomic ions. Yeah, so those guys in that chart, everybody loves those guys. So when you look at an equation that contains polyatomic ions on both sides of the arrow, so for example here, nitrate and nitrate, I would highly recommend maybe not doing the element for element sort of table, because what happens with polyatomic ions, as we talked about, you got to put parentheses, right? You got numbers on the outside. You're doing a lot of multiplying in, multiplying out for every individual element. You can absolutely do it with every individual element, but it does probably increase your chance of error as you're kind of multiplying in and multiplying out. So a lot of times when you have polyatomic ions on both sides of the arrow and they're exactly the same polyatomic ion, that's usually the best place to start, and just balance them as like whole units. So for example, if I was going to do this, I might forego the table here up front and go, I have two nitrates there on the left, and on the right, how many nitrates do I have? 1. So that's where I'm going to start. I'm going to fix that by putting a 2 here, and that's now going to give me 2 nitrates on the right. And when you do this method, in this example, I went and fixed the nitrate. Where you should go next is basically the other element that's there. So in this case, the other element is potassium that now becomes a 2, right? And that's where I should go to the other side. On the other side, I only have 1. I'm going to fix that by putting a 2, right? And since I just fixed the potassium, I now should go to the iodine, which is a 2, but look, I'm done. I walk away happy and a lot quicker in a lot of situations. So oftentimes when you're dealing with polyatomic ions, it's much easier to keep them together, balance them as like whole units. And a lot of times what will happen, just like that, everything will sort of fall into place if you sort of do it right. Again, you can still go element by element if you choose to, but there's a lot more maybe chances of maybe some errors and stuff like that. Question on that? All right, so why don't you try some here? Let's go with, I'm gonna try not to write the balance equation as I put them up here. I suppose that'll be good. Let's do this guy here, which looks like fun. Let's see here. A little bit of that. A little bit of this. Why don't you see how you're doing? So let's get on these first ones. I do see some polyatomic ions that are the same on each side. In this case, we actually have 2 different polyatomic ions on each side. And you really could start with either one. Sometimes they'll both work out okay. Sometimes, you know, maybe it won't work out so okay. You may have to go back. But for me, I'm going to actually start with the sulfate because it just seems easier. I got 3 on one side and 1 on the other, rather than I got 2 and 3, which is going to require me to put a couple of numbers on both sides. So I'm going to start with the sulfate. Once again, I'm going to keep it together. I got 3 on the left-hand side, only 1 on the right, which means I do need to put a 3 here. When I do that, the next place I want to go is the other element that was with sulfate, which is calcium, that now has a 3 on the right-hand side, and now we'll need a 3 on the left-hand side. Now that I just did calcium, I now want to look at the nitrate, which will now have how many? 6. So to give me 6 nitrate on the right, I need to put a 2, and that gives me 2 iron, which again is what I need in this case, and I am balanced. So probably a lot easier than trying to kind of in and with every element, but again, you can do that. but definitely with these polyatomic ions, probably keep them together and try to balance it that way. Any questions on that there? Let's take a look at the next one. Same deal. We got a sulfate here and a sulfate here, and a nitrate and a nitrate again. Once again, in this case, I'm going to start with the sulfate. I'm going to go with 3 for the sulfate, and that will then give me 3 barium, which is where I want to go next. I'm going to put a 3 there. That then will give me my 6 nitrate, which means I want to put a 2 there. And again, at this point now, I am balanced. Again, a lot quicker than probably going each element by itself. Any questions on that there? All right, layer this one, we really don't have polyatomic ions. So I might go back to a table approach here, and each element by itself, carbon, hydrogen, and oxygen. We got 4 on the left, 1 carbon on the right. We got 10 hydrogens on the left, 2 on the right, and 2 oxygens on the left, and 3 on the right. So here I'm going to start with the easiest, which looks like carbon in this case. I'm going to put a 4. That will give me 4 carbons. We'll still have 2 hydrogens. We now have 8 oxygens there, plus 1 more, makes 9, if I am not mistaken. At that point, we would then go perhaps with our hydrogen, which is only in one place. So that would be the easiest. To fix the hydrogen, I need a 5 right about there. And that is going to give me here 4 carbons. We got 10 hydrogens. And now I got 8 and 5. That's like 13, I think, in this case. At this point, right, we basically need to turn our 2 into a 13. So this is another case where a fraction would be a good choice. Once again, the number that goes on top is the number we need. So we do need 13. So that is what I want to go up on top with. The number on the bottom should match this number, which is 2. And now we should have something that should work for us. 4 carbons, 10 hydrogens. And once again, when you take 13 halves times 2, the 2's cancel and leave you 13 there for the oxygens. Can I leave the fraction? No. So again, just like the last one, we need to clear the fraction by multiplying everybody, not just the fraction, by the 2. And if you do that, that will get you, I'll go above 2C4H10 plus 13O2 gives me 8 CO2 and 10 H2O. And once again, at this point, should still be balanced. We have 8 carbons on each side. We have 20 hydrogens on each side, and we have 26 oxygens on each side. We got 16 oxygens here and 10 here, which will give us 26. So we're balanced. So a couple of fun things on balancing. May have to use a fraction, which is good. Just got to clear it. And again, if you have some polyatomic ions, something looks scary, and a bunch of those guys, keep them together and sort of balance them as whole units. Questions on balancing equations? Okay, we're going to continue on here, and we're going to react or talk about types of reactions now. And these are different ways that you could classify reactions taking place. And as we will see, there are multiple ways you could classify the same reaction depending on sort of what you're looking at. So we will see, for example, one particular reaction that you could classify in like 2 or 3 different ways, depending on sort of what you're looking at. But overall, when we talk about reactions, there's really 2 big categories of reactions that pretty much every single reaction falls under. And those 2 are a redox reaction. And a redox reaction involves an oxidation and reduction taking place, which we will talk about. But essentially, it involves a transfer of electrons. So there's really a transfer of electrons that are happening in this particular case. And that's sort of a big classification of reactions, which are sometimes referred to as redox reactions. Underneath that big classification are more specific ways you could classify a reaction, as we'll talk about, things like synthesis reactions, decomposition reactions, single replacement reactions. The other big category of reactions are what are known as double displacement reactions. And double displacement reactions basically have this general setup where you have basically two ionic compounds that are reacting with each other. And when you have two ionic compounds reacting with each other, basically what will happen is if a reaction does take place, the two positive guys will basically switch partners. So we will make two new ionic compounds on the product side. And the result of this sort of double displacement reaction will basically result in one of two things occurring. Perhaps you may make a solid. One of these guys may make a solid, which is sometimes referred to as a precipitate. And that will be what is sometimes referred to as a precipitation reaction. And that is some type of precipitate is formed. And a precipitate is sometimes abbreviated as a PPT, and that means basically you made a solid. The other very common thing that will occur in a double displacement reaction is you will make water. And really, when you boil down pretty much all reactions, those are really the three reasons why reactions take place. Is basically either you are going to make a solid, you're going to make water, or you have some electrons being transferred. Those are basically the three real reasons why a reaction will take place. If none of these three things occur, pretty much you might not get a reaction to actually happen, which does happen. You can mix things together and nothing happens. There's no reaction. Everybody's just floating around in the solution. Nobody's reacting with each other. You basically have what you started with. So they're not really reactions, but you can toss things together that really nothing will work. So pretty much all reactions that sort of work, that actually are chemical reactions, will boil down to one of these three things basically happening. And that's really what sometimes, as we will see, was referred to as the driving force for a chemical reaction is I want to make a solid, I want to make water, or I want to transfer some electrons. And pretty much that covers almost every reaction that you will sort of come across. All right, so we're going to start with, I think, redox reactions and talk a little bit about these guys. Then we'll talk about some of the double displacement reactions and different ways to classify. So let's talk about redox reactions, which are oxidation and reduction reactions. And a lot of times this occurs when you have a metal and a non-metal together. And as we talked about in an ionic compound, when you have a metal and a non-metal together, the metal typically will transfer, right, our electron over to the metal, to the non-metal. And that will result in our metal becoming a cation, right, and our non-metal becoming an anion. And in the simplest case, in an oxidation reduction reaction, that is always what's going to happen. Now, you can have situations where electrons are actually transferred between, say, metals, and that can occur as well. And so when we talk about oxidation reduction, there's a couple of definitions that we see. Typically, in most cases, when we talk about oxidation, especially in inorganic chemistry, which is sort of what we're doing now, it means that we have lost electrons or you lose electrons. And when we have reduction, it typically means that you gain electrons. So there is a simple way to sort of figure out what is being oxidized, what is being reduced, and it has to do with when I lose electrons, do I become more positive or more negative? Yeah, because we have less electrons, right? More protons, right? So we become more positive. And when I gain electrons, I become more negative, right? Because we're gaining negatively charged electrons. So you could use like a very simple like number line type situation where you got 0 and like to the right there are positive numbers, right? To the left are negative numbers. And if you look at an element on, say, the left-hand side of the arrow versus it on the right-hand side of the arrow, and you look at really what is called as the oxidation state, but if we will just call it charge for our purposes here. If you look at sort of the charge on the left-hand side of the arrow for that element, and like the charge or the oxidation state on the right-hand side of the element, and you see that it is kind of moving in this direction, more the positive direction, then that thing is going through oxidation. And if you look at the charge on the left-hand side or the oxidation state on the left-hand side of the arrow and the right-hand side of the arrow for an element, and it's kind of moving in this direction, becoming more negative, it is going through reduction. So that's a really simple way just to kind of figure out what's being oxidized, what's being reduced. You simply kind of go by what their oxidation state or charge is on one side of the arrow or the other. When you have an element that is by itself, that is not combined with anybody else, like anybody you take from the periodic table, that is, again, by itself, uncombined, do those things have charges? They do not. So things only really get charges in a sense when they hook up with other things, like when metals and non-metals, right, come together. That's when these things become positive or negatively charged. When really two non-metals come together, that's also when they sort of get a sort of charge, or an oxidation state is really what it's referred to. So if you have any type of element that is not combined with any other element, it will have sort of a zero when you're sort of thinking about your number line where to start. And again, if you have like an ionic compound, then you could think about it as having a actual charge. So let's take a look at this, and this is an example of this. We have sodium metal by itself, and by itself, it has no charge. That is chlorine, right, which is a diatomic molecule, and that is naturally how it comes as a 2. It also really has an oxidation state of 0 or no charge. But when we put sodium and chlorine together to make sodium chloride, that's an ionic compound, right? And although the formula doesn't have a charge, it is made up of two things that do have charges, right? The sodium in this case has what type of charge? +1, group number 1, right? Cl has a -1 charge, group number 7, like we talked about with naming. So now if we look at what's happening here in our number line, for example, if we take the sodium on the left-hand side, it started at 0, right? On the right-hand side, ended at +1, which is moving in that direction, becoming more positive, which means here in this case, the sodium is going through oxidation, yeah? If we look at the chlorine, it started at 0, I'll go below. And on the right-hand side, it ended at -1, which is moving in this direction, right? More negative, which means the chlorine here is actually going through reduction in this case. And what is really happening in this reaction is the sodium is tossing some electrons over here, and that is a transfer of electrons, which, as I mentioned before, is one of the reasons why a reaction is taking place. So when you put sodium and chlorine together, it will make sodium chloride because they are transferring electrons, and they will want to do that because of those periodic trends we talked about, where sodium will be very happy to get rid of its electrons, right? And chlorine, which is a non-metal, has all those trends of I want to pick up the electrons. So that is again what's happening here. This can be classified under the big umbrella of a redox reaction, which again is those electrons basically being transferred. Any questions on that there? So this is an oxidation reduction reaction. If we look at down here, we have magnesium and oxygen, a little magnesium oxide. That's a popular one they usually do in labs. They like take a piece of magnesium ribbon and they put it into the fire, and they say, observe what happens without looking directly at it. By the way, if you do that this week, don't look directly at it so you don't get spots in your eyes. It's going to be very, very bright. But it is also a redox reaction. So if we look at the magnesium, that's magnesium by itself, not combined with any other element, which means it has a 0 in terms of its oxidation state or charge. That is oxygen, which also comes as a diatomic molecule, not combined with any other element, which is also means it has really no charge or oxidation state. But when we put the magnesium and the oxygen together, once again, those two things do have charges. Magnesium has what type of charge? Group number 2, which means it is +2. Oxygen is group number 6, which means it is -2. That's also like we talked about with naming, why there's just one of each, right? +2, -2 gives you 0, right? When you put that together. So again, if we were to do our just very simple number line to figure out what is happening, if we look at the magnesium, it started at 0, ended at +2, becoming more positive as it goes from left to right on the reaction. It means it is going through oxidation. And if we look at the oxygen started at 0 and ended at -2, which means it's becoming more negative. It is going through reduction. And again, what's happening here is the same thing. He's going to send some electrons over. And again, he's going to lose some electrons, gain some electrons, transferring electrons, basically what a redox reaction is. By the way, some people remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig, which is oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig and he goes grr, and you don't have to choose. You can just use them all together. You'll be fine in that case. Why not? All right. So in each of these cases, these are oxidation reduction reactions. They can be classified in sort of the big classification as redox reactions. By the way, like I said before, it doesn't necessarily always has to be, metal and a non-metal sort of happening. So let's just say, for example, I had let's say on one side of the air I had copper +2, and on the other side I had copper +1. Is the copper being oxidized or reduced in this case? So let's see. So the copper is starting at +2, which is over here-ish, and it's ending at +1, which means it's going in this direction, and it's actually becoming more negative. Even though they're both positive, it's becoming more negative, and it is going through reduction here and being reduced. Very good. So it went from +2 to +1. So as I mentioned before, you don't necessarily have to even have a non-metal in the mix. A lot of redox reactions, by the way, which are electrochemistry, galvanic cells, batteries, those type of things, involve basically metals and metals, basically exchanging electrons and transferring electrons from one side to the next and stuff like that. So it works the same, the little number line for things that are, have charges on both sides as well. Any questions on that there? Yeah. It does. I just use it as an example of just the ions. Obviously there would be more things involved and stuff like that. Yeah. So if you had something like this, like all right, so what is being oxidized? What is being reduced in this case? All right, so let's just identify where everybody's starting and ending. In this case, zinc on the left-hand side has no oxidation state, right? It's by itself, basically just a piece of zinc metal. It is 0, right? That is H+, which means it's +1. And over here, that's zinc with a +2 charge, which is +2. And hydrogen over here is by itself naturally how it comes, which is 0 in terms of here. So if we look at the zinc is starting at 0 and ending at +2. So yes, I think I heard it earlier. It is being oxidized, right? Or going through oxidation. The nice thing, by the way, about redox reactions is if you can identify one thing in terms of what is being oxidized or what is being reduced, by default, the other guy's got to be doing the opposite thing. They always occur together. So if somebody's being oxidized, there's got to be somebody there being reduced. So those things always occur together. So for example, here, if you were able to feel good about that zinc is being oxidized, by default, that would mean the H plus there has to be reduced. And we can see it with the H plus. If we look at the H plus, it starts at +1 and ends at 0, which means it's going in that direction, becoming more negative, and is being reduced or going through reduction in this case. So that's also one of the nice things about redox reactions is all you have to do is correctly identify one of them, and the other guy's doing the opposite thing because it always occurs together. So you'll never have anybody being oxidized without anybody being reduced. The reason for that is the electrons need to go somewhere, right? So if somebody loses electrons, somebody has to gain electrons. So they always happen together. Any questions on that there? All right. All right. We will see this definition a little bit later on in the semester when we get into organic chemistry. But sometimes when we're dealing with organic chemistry, which involves a lot of nonmetals and nonmetals, it's sometimes easier to look at whether or not somebody gains hydrogen or oxygen or loses hydrogen or oxygen rather than look at charges. So another definition of oxidation is as somebody goes from the reactants to the products, they will gain more oxygen. And if somebody goes from reactants to products and they lose some oxygen, then they are being reduced. Hydrogen works the same way. Do I have that? I do. Next, we'll look at next. But so, for example, here, if we look at the sulfur, sulfur has 2 oxygens there, gains an oxygen, so sulfur is being oxidized. By default, that means here that the oxygen would be reduced. Here, copper has oxygen, has no oxygen as it goes to the other side, so it loses oxygen, and that would be that is reduced. And again, by default here, the hydrogen would be oxidized. By the way, since there is copper and a metal there, you could also do the number line on that one. The copper here has what charge? Does not. It does have a +2 because oxygen in this case is -2. That is copper 2 oxide, right? Over here, this is copper metal by itself, which means it has 0. So again, if we slap that up there on our number line, we are starting at +2, ending at 0, which means again, it is becoming more negative and going through reduction, which then would tell us, like we just determined there, that that guy is going through oxidation. So if you do have a metal, you can still kind of do the number line thing. But a lot of times when we're dealing with nonmetals, especially in organic situations, it's a lot of times easier to look at hydrogen or oxygen. Other definitions that we'll see more of really in organic chemistry, oxidation is the process where somebody will lose hydrogen. And in most cases, it's actually like H2 in most cases. And reduction means somebody gains more hydrogen. So there's basically 3 definitions of oxidation and reduction. Oxidation means you lose electrons, you gain oxygen, or you lose hydrogen. Reduction is you gain electrons, you lose oxygen, and you gain hydrogen. So those are 3 definitions. Once again, most of the time in sort of non-organic chemistry, we look at the electrons and the losing and gaining. And organic, we'll see that when we get there. Those are very common definitions, hydrogen and oxygen in terms of oxidation and reduction. Any questions on that there? So here, obviously, the carbon has hydrogen and has no hydrogen on that side. So it has lost some hydrogen. So it's going through oxidation. By the way, the other definition there is carbon also gains some oxygen, right? Which also tells us it is being oxidized as well, right? So you can use the other definition as you go through there. And then our oxygen here gains some hydrogen and is being reduced in that particular case. So I say we will probably see more of that in organic. So we won't focus too much on that right now. So let's talk about classifying reactions more specifically. So we have these 2 sort of big classifications of redox and double displacement reactions. The 3 driving forces, as I mentioned before, a solid being formed and water being formed, those fall under the double displacement reactions. and electrons being transferred again fall under sort of the redox category of reactions. So let's take a look at some more specific classifications. First one is a synthesis reaction or a combination reaction. This is a redox category. So synthesis or combination is pretty much what the name sounds like. In a synthesis or combination, essentially you take two things, make one thing, put them together, combination, combo it, right? So two things make one thing is your classic way that you could recognize a reaction as being a synthesis or combination reaction. Here's H2 and O2, two things make one thing. So that is a synthesis or combination. Two things make one thing is a synthesis or combination reaction. Each of those things are still redox reactions, because if we look here, that is zero. That is zero. Hydrogen here is +1 and -1 and -2 in this case. That's better. And again, if we look, hydrogen is going from 0 to +1, which means it's becoming more positive and being oxidized. The oxygen is going from 0 to -2, which means it's becoming more negative and being reduced in this case. And then obviously we did the same thing for the sodium chloride earlier. That also is a redox reaction that's happening. So each of these fall under the big redox umbrella. A more specific classification for each of these would probably be a synthesis or combination reaction in that particular case. So the next classification of reactions is really the opposite of this reaction, and that is a decomposition reaction. And you can really think of a decomposition reaction as essentially the opposite of putting it together. This also falls under the umbrella of a redox reaction here. So in a decomposition, one thing makes two or more things. So combination, you put it together to make one thing. Decomposition, you basically break it apart into a few things. So one thing makes many. So here, if we run an electrical current over water, you will get hydrogen gas and oxygen gas that will form. It's known as the electrolysis of water. One thing makes two things. This is the decomposition of mercury 2 oxide, and it will make mercury liquid and oxygen. Again, one thing makes two things. That is sort of what you would look at to recognize it as a decomposition reaction. Basically the exact opposite reaction of putting it together, which is the synthesis reaction. These are still redox reactions. So if we look at this guy here, this is mercury 2, and that is -2, 0, and 0 in this case. In this case, what is being oxidized? So let's take a look at the Hg first, right? Hg on the left is +2, right? And on the right-hand side, it is 0, which means it is moving in the more negative direction. So in this case, the Hg is actually being reduced. Yeah, this guy is being reduced, which by default means the oxygen here is being oxidized. And we see it if we look at the oxygen. Oxygen is starting at -2, which would be here, and ending at 0, becoming more positive in this case. So same thing with our water. In this case, the water is actually opposite of putting it together. In this case, what is being oxidized and what's being reduced? In the case of the water, which is our H2O, that is +1 and -2 going to 0 and 0, basically. So in this case, our hydrogen is going from +1 to 0, which means it's actually being reduced. And the oxygen, again, here is going from -2 to 0, which means it's being oxidized. And that is opposite of what happens in a synthesis reaction, right? Because this is the reverse, basically, that's happening. In the synthesis reaction, when we looked at it, right, it was the hydrogen going from 0 to +1 being oxidized. and the oxygen being reduced. And again, it's opposite because we're going backwards. Basically, we're actually putting the electrons back, if you want to think about it that way, kind of throwing the electrons back the other way. Question on that. So decomposition, one thing makes many, and it is technically under the big category of redox reactions, but can be more specifically classified as a decomposition reaction. And most people probably would classify these guys as decomposition reactions. But again, they still are basically the electrons being transferred, which is really why these reactions are taking place, because we have those transfer of electrons. Question those two there. Next type of reaction is a single replacement reaction. And in a single replacement reaction, this also is a redox reaction. So this also falls under the big umbrella of redox. And in a single replacement reaction, basically there's two types that could happen. You could have A plus B, C. This is an ionic compound, so a positive and negative guy. This, for example, could be a metal, which has no charge. But when metals do have charges, they become positive or negative, which means when they come in, it will actually kick out the positive guy. So that's a good way to remember that. When a metal comes in this type of reaction, it will kick out the positive guy that's there. And at that point, it will actually gain a charge and make a new ionic compound. And what will happen is the guy that had the positive charge originally will come out and have no charge. And what's happening here is really transfer of electrons is causing that to occur. You could also do this where A is actually a nonmetal, and it would have no charge to begin with. And just like the metal, when nonmetals make a charge, they become negatively charged, which means it will go in and kick out the negative guy. So in these single replacement reactions, they come in and kick out the guy that has the same type of charge when they do get a charge. And we will make a new ionic compound, look something like this, and our guy will come out with no charge. And that's what we see here. We have zinc, which is a metal. This is hydrochloric acid, which is basically a ionic sort of compound. And the zinc will come in and kick out the hydrogen in this case. When it does so, hydrogen comes out in its natural state of hydrogen gas. So if you do this reaction, you'll see some bubbles. Bubbles is an indication that a gas has been made. And those bubbles that you would see in this case would be the hydrogen gases basically being made. It will then, at that point, zinc will gain our +2 charge, and our chloride here will be -1. This again is still a redox reaction. This is actually the one I did on the other page. The zinc goes from 0 to +2, right? Which means the zinc is being oxidized. The hydrogen here is going from +1 to 0, which is being reduced. What's happening with the Cl? Stays the same, is what we like to call a spectator ion. It's just swimming around watching what's going on, right? That's what a spectator does, it just watches. And that's essentially what's happening with the chloride. Nothing's really happening with the chloride. It's just kind of floating around, just there to kind of balance out charges, but it's not going to make anything in terms of the reaction. Once again, here in each of these cases, this is electrons being transferred, which is why they fall under the big umbrella of redox, but they are more specifically classified as single replacement reactions. Most people would do that. Now, if you did something like Cl2, for example, plus a little sodium bromide, this is 0 and plus and minus. The chlorine should come in and kick out which one? Yeah. And when it does, it makes sodium and chlorine coming together, which, by the way, when I write sodium and chlorine coming together properly, what should the formula be? It should be NaCl, right? Because sodium is +1, Cl is -1. This is what I was talking about earlier. I'm just going to tie it all together right now. So what I was talking about earlier, we want to make sure we get the right formula first, not balance, right? There is no such thing, by the way, as Na2Cl2. Yes, that is like an X. So we want to make sure you get the right formula here. The Br is going to come out by itself, which would be Br2 in this case. That is one of those diatomic molecules that are elements. At this point, now that I have the proper formula, is it balanced? Is not. This is then when I should balance, right? Put like a 2 there and a 2 there, and now I'm balanced. So that's what I was talking about before. If you have just a reactants, you want to predict the products. You want to make sure you get the right formulas first, then balance it. Don't do them together. You will get the wrong formulas and not have it balanced. But more importantly here, we have a redox reaction that's happening. In this case, what is being oxidized? By the way, this is +1, right? That's -1, that's -1, and that's 0. So what is being oxidized here? It is the bromine. I think I heard somebody maybe whisper. Yes. So on the left-hand side, we have bromine here with a -1 and ending at 0, right? Becoming more positive. And the chlorine started at 0 and ended at -1, which is heading in that direction, right? Becoming more negative. So these are two nonmetals where you can still apply electrons being transferred and a redox reaction happening. You'll do that later on in lab, and when we get to organic, I think maybe you do it at some point, this particular one. Now, in order for this reaction to actually take place, whatever is coming in, either the metal by itself or the non-metal, has to be more reactive than what it's replacing. So if it is not more reactive than what it's replacing, the reaction will not happen. So for example, if you took I2 and you wanted to react it with sodium chloride, this reaction will not take place because iodine is actually less reactive than chlorine. For the halogens, which is group 7, reactivity actually increases as you go up. So anybody higher in that group 7 will replace somebody lower. So what I mean by that is chlorine is higher than bromine. So that reaction will take place. But iodine is lower than Cl, which means it's less reactive. It actually will not take place. So for group 7, actually is your, what is sometimes referred to as your activity series for your nonmetals there for group 7. It does increase as you go up. For example, instead of zinc, if you use copper and you try to do a little reaction with hydrochloric acid, not going to work because copper is less reactive than hydrogen, and the reaction will not take place. Years ago, they used to do an old experiment where I taught where they would take old pennies and new pennies. Yes, old pennies are made up of pure. New pennies have what inside? Zinc. Outside is copper. So what you do is you file your pennies to expose the inside, drop both of them into hydrochloric acid. When you come back, only one survives. The other one's hollow inside. It basically will react with everything inside and stuff like that. They don't do that anymore because you're not supposed to destroy money, but they don't do those experiments. But there are certain reactions that won't take place. And an activity series is what we use for single replacement reactions. And a basic activity series is really just a list of elements. Usually there's hydrogen in the middle and a bunch of lists of other elements that are there. And anything higher on the list will replace anybody lower on the list. Anybody lower on the list will replace anybody higher on the list. And that is, again, what is sometimes referred to as an activity series as well. Question on that there. All right, so let's talk about another type of reactions. And now what we're going to talk about here are actually double displacement reactions. So double displacement reactions. And in this case, that is what we talked about earlier. We have a positive, negative guy, positive, negative. And again, these two guys are going to switch partners, basically. And we'll make two new ionic compounds. And in the case of a precipitation reaction, one of these guys will make a solid. And that's what we see here. We have a positive, negative guy. Positive, negative guy. I know that's going to be a double displacement reaction. So they are going to switch partners. Once again, when we go to the other side, we want to think of this as K+, which is what potassium is. That is chromate, which is a polyatomic ion. That is barium, which is +2, and nitrate, which is -1. That is why when we put these together, we get KNO3. We don't get like K2NO3 2. Again, Make sure you have the right formula first, just like you're doing nomenclature, and then balance. That's also why when we put these guys together, we just need one of each, right? +2 and -2 gives us 0 when we put it together, which is how we get to this formula here. In this case, that barium chromate will make a solid. So this is what is referred to as a precipitation reaction. That is a more specific classification of a double displacement reaction. This is the second reason why a reaction takes place. I just made a solid. And that is really what is happening here. What is really happening here when you throw these two solutions into a beaker, you have barium floating around, you got potassium floating around, you got chromate floating around, and you got nitrate floating around. These two guys will like each other and come together and make a solid. These other two guys are just floating around still. They're what are referred to as spectator ions. They're not doing anything. They're not making the solid that's being formed in this case. So whenever you see two ionic compounds together, it's a double displacement reaction. And that's different than a single replacement where you have only one ionic compound. So that's how you can tell the difference between those two. Double two, right? So you need two ionic compounds, two positive guys switch partners, and that's what you get on the other side. And that's what we see here. Again, we get this double exchange that's occurring, and we get this solid that's formed, which is, again, a precipitation reaction. Now, this type of reaction is an acid and base reaction. This is hydrochloric acid, which is an acid, and this is a base. And whenever you take an acid and a base together, you get two things. You get your friend water, which is not a trick question, right? H2O. And you get this guy, which is sometimes referred to as a salt. A salt is a fancy word. I don't know how fancy it is for an ionic compound, basically. And that's what we have here. This is still a double displacement reaction. That's a positive, negative, positive, negative. So this also is classified under the big umbrella of double displacement. And whenever you have an acid and base that comes together, the water is always made from the H from the acid, the OH from the base. That is always where the water is made from. And the salt, or the ionic guy, is made from the other two things that are left over, K plus and Cl minus will make our salt. So this is still ultimately what is happening is our positive guys are switching partners, basically. So they are switching partners, and we will make water always. So frankly, you could just put your hand over the H for the acid, OH for the base. What's left, put them together correctly based on nomenclature. So this is a double displacement reaction. This is also sometimes called an acid-base reaction or an acid-base neutralization reaction because frankly, you made water, which if you remember is the third reason why a reaction takes place is to make water. So double displacement reactions account for solids being made, water being made, redox reactions account for all the electrons being transferred. And again, that's why those are kind of like the two big umbrellas, double displacement and redox, where you could get more specific in terms of your classifications underneath. Any questions on that? All right, one last classification to finish it up on. Remember, that is fast, so just relax. You're good. You got plenty of time. It's a long week. We'll see each other again for twice this week. I know it's sad. All right, last classification is a combustion reaction. I'm just going to entertain myself. It's okay. So a combustion reaction, most people, when they talk about a combustion reaction, is probably going to be referring to what I like to call an organic combustion reaction, which is like what the gas comes out of here and you light your Bunsen burner. So an organic combustion reaction always has this, some type of organic compound which contains either carbon, hydrogen, maybe oxygen, which is what we have in each of these cases. It will always have O2 and make CO2 and water. So that's like a no-brainer. You see like an organic guy, you got O2 and they're like, what's on the other side? CO2 and water is what you want to put there in this. The definition of combustion is more generic as well. And by the way, this also falls under redox usually. And This general definition of combustion is all you frankly need there is our friend oxygen to be there on the left-hand side. And you could classify it as a combustion reaction. So what that means, for example, if we look at an equation we saw earlier here, Mg plus O2, do not watch it so closely, but make sure you observe what happens without looking directly at it. Yes. We have here a redox reaction, as we talked about, correct? We have here two things that make one thing, which is a synthesis reaction or combination. And dare I say, I see oxygen, which means you could classify this one as a combustion reaction, yeah? So this one reaction could be classified 3 different ways. I would say most people would probably classify it as a synthesis or combination reaction, but it does fall and meet the criteria of all the other 2 classifications as well. So when you're going to classify reactions, because there are multiple ways you could classify the same reaction, the best one to choose is what is best for that situation of your options, what you're looking at. But just be aware you can classify these reactions in different ways. So just to finish out one more time here, redox reaction is our big classifications that involves our electrons being transferred. Underneath that classification, you have your synthesis reactions or your combination. You have your decomposition reactions. You have your single replacement. And you have your combustion reaction. The other big classification is our double displacement, where underneath there you have more specifically a precipitation reaction, which means you made a solid, or you have your acid-base reactions, which means you made water. And once again, making water, making a solid, and electrons being transferred is really the basis of pretty much all reactions that you will come across in most of the times. Any questions on reactions, classifying reactions? All right, let's wrap.